Hello again. In today's lesson, we're going to look at section 9.2, which is titled Tests Involving the Mean Mu for Large Samples. This is section 9.2. If you have not read and looked at and paid careful attention to the things that are in 9.1, stop this video and go do that now, because otherwise you may be considerably lost, and I don't want that. When you were reading section 9.1, the things that I was hoping that you would come across were the difference between the null hypothesis and an alternate hypothesis. That the idea behind hypothesis testing is that we are trying to see if we can reject the null hypothesis on the basis of our sample being too far from the mean. Now the big question is, where exactly is x bar on this distribution, on the x distribution, and is it too far away from mu? How do we decide that? Well, it's through confidence levels, just the same as we were looking at in chapter 8. For hypothesis testing, confidence levels are usually either 95 or 99%. We don't typically talk about 80% or 85 or 90% confidence levels. When we have a 95% confidence level, we define the variable alpha as 0.05. If we're saying that we have a 95% confidence level in something, we're saying that 95% of our samples should get us into an interval or should show something in particular. Alpha is the reverse. It's the probability that we didn't get what we were expecting. So when the confidence level is 95%, alpha is 5%. So 0.95 converts to an alpha of 0.05. In the same way, a 99% confidence level, alpha is 0.01. This part's really important. You always, always, always choose alpha before you test the hypothesis. Otherwise, you're cheating. Think about it. If you are somebody who is not typically, you don't typically run long distances, and you decide that you want to run, you want to be a better runner, more endurance, you'd set a goal for yourself each day before you go out and run. You wouldn't say, I'm going to run for a little while, and then when you're done and you say, oh, look, I ran 2 miles today. That's good enough. No, you'd set the goal ahead of time. So always choose alpha before you test your hypothesis. You want to have that goal. You want to have that target to hit. Now, when we talk about the null hypothesis being mu is equal to some number, and k is just some number, don't get any great ideas out of the fact that it says k. K is just a number. For example, mu equals 10. Then the null hypothesis is has one of the following three structures. We could say that mu is less than k. We call that a left-tailed test, for reasons that'll be obvious on the next couple of slides. If our alternate hypothesis is that mu is greater than this number, that's a right-tailed test. And if our alternate hypothesis is that mu is not equal to this number, whatever k is, it's a two-tailed test. It's always going to be the same k for both the null hypothesis and the alternate hypothesis. So if the null hypothesis is mu equals 10, the alternate hypothesis might be mu is less than 10. It would never, ever, ever be something like mu is less than 20 if the null hypothesis is mu equals 10. The two numbers have to be the same. On a left-tailed test, we are testing whether or not we can get a z-score based off of x bar to fall into the shaded area. For a left-tailed test, that's the area over here on the left, this blue shaded area, or in this picture, the blue shaded area right here. And I'm going to erase those arrows because they are blocking. When I find my eraser, I'm going to erase those arrows because they're blocking the negative signs on those critical z-scores. We will reject the null hypothesis if the z-score that we get lands us in the blue region. In other words, for a 5% significance level, alpha equals 0.05, if we can get a z-score lower than negative 1.645. And for a 99% confidence level, when alpha is 0.01, to get a z-score that falls lower than negative 2.33. And if you're saying, gee, I've seen these numbers before, 1.645 and 2.33, I've seen these before. Yeah, we've been looking at them repeatedly for the last couple of chapters, and we're going to continue to. And they also happen to be the infinity row on table 6 for your reference, which, spoiler alert, we're going to be using table 6 again in upcoming lessons, just not this one. Right-tailed test works in the exact opposite way as far as where we are on the normal curve of the right-tailed test. We're trying to fall into the blue shaded region on in a right-tailed test, we are looking to fall into the shaded region on the right. Left-tailed test, we fall on the tail on the left. Right-tailed test, we fall into the tail on the right. They're the same z sub zeros that we looked at on the last slide, except this time they're positive. Positive 1.645 for a 5% significance level, 2.33 for a 99% confidence level. In other words, a significance level of 1%. For a two-tailed test, where we're saying all we care about is that mu is not equal to k, that we're found convincing evidence that it isn't true, we can be either in the left tail or the right tail. For a 5% level of significance, that means that the two blue tails have to add up in area to 0.05. And since the entire normal curve is symmetrical, those two areas have the same boundary, except one is negative and the other one is positive. So in a two-tailed test at a 5% level of significance, if we can go lower than negative 1.96, we will reject the null hypothesis. If we get a z-score that is higher than positive 1.96, that would also allow us to reject the null hypothesis. At a 1% level of significance, those boundaries are negative 2.58 and positive 2.58. If we land in the middle somewhere, we are not able to reject the null hypothesis. We say that we fail to reject. Here's an example. No, don't copy this down. The important parts we'll get through here as I read it real quick. St. Louis Zoo wishes to obtain eggs of a rare Mississippi River turtle. The zoo will hatch the eggs and raise the turtles, blah, 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 blah. Past research has shown that the size of the turtle eggs are normally distributed with a population mean of 7.5 centimeters and a standard deviation of 1.5 centimeters. The rare egg is the only one with a mean of 7.5 centimeters. The mean lengths of eggs from all the other species known to exist in the area are all bigger than that. They're all longer than 7.5 centimeters. That's an important fact. The eggs of all the local species have the same standard deviation. That really helps us out here. In all cases, the standard deviation is 1.5. After searching for some time, Carol found a nest with 36 eggs. Oh, looks like we've got a sample size. The way the nest was constructed makes her suspect it was made by the rare turtle. The mean length of this collection of 36 eggs is 7.74 centimeters. There's your X bar. Since it's bigger than the population mean, Carol is a little worried that these eggs may come from one of the more common species. We want a significance test to figure out if she should take those eggs back with her to the zoo. First thing we better do is define our parameter. What is mu? In these problems, we're always setting up the variable of interest as being mu and x bar. We'll come back around to p and p hat in a future section. In this case, mu is the mean length of the eggs from the rare turtle. Set up our null hypothesis and our alternate hypothesis. The null hypothesis is that mu is actually 7.5 centimeters. That, in other words, that we have found a nest from this rare species of turtle. The alternate hypothesis is based on that we did not find a nest of rare turtle eggs, that they're more common ones. And we had said in the last slide that all the other turtles in the area, that their eggs were on average larger than 7.5. So we'll say that the null hypothesis is that mu is equal to 7.5 centimeters. The alternate hypothesis is that mu is greater than 7.5 centimeters. Since the alternate hypothesis is based on a greater than, we are doing a right-tailed test. And I don't think that we've said so far what the level of significance of this test is. I'm going to tell you right now that we are testing at a 1% level of significance. That means that we are looking for a critical value for z. This critical z is at positive 2.33. So if we can get a z-score that falls in here, we are happy. It's got to be greater than, the z-score that we get has got to be greater than or equal to positive 2.33. And if we get that, we will reject the null hypothesis and run with the alternate hypothesis. If our z-score is lower than 2.33, then we are not in the right-hand tail, and we will fail to reject the null hypothesis. Finding that z-score, we've done this many times. X bar minus mu over sigma divided by the square root of n. X bar is 7.74, came straight out of the problem that you were given. Mu is 7.5, gives us a numerator of 0.24. Denominator is sigma over the square root of n, 1.5 divided by the square root of 36. Plug all those numbers in, you get a z-score of 0.96. Is 0.96 greater than 2.33? It is not. And because of that, we fail to reject the null hypothesis. If we had a z-score that was bigger than z sub 0, if, for example, we got to the end of the problem, and instead of 0.96, this number was 2.8 or 3.4, in that case, we would reject the null hypothesis. And in that case, we would have said that our results were statistically significant. In this case, our results are not statistically significant. We have failed to reject the null hypothesis. This last part is a super important point. You never, ever, ever accept the null hypothesis. You are testing whether or not to throw it away. You may think of the rejecting or not rejecting the null hypothesis almost as if we are going to trial and you are being prosecuted. At the end, the jury comes back and they do not find you innocent. They find you guilty or they find you not guilty. If they found you guilty, there was enough evidence to reject your claim that you didn't do it. If they find you not guilty, they are not saying you didn't do it. They're saying there's not enough evidence that you didn't do it. In the same way, rejecting the null hypothesis means we have enough evidence to push aside the initial claim. And failing to reject the null hypothesis means we don't have enough evidence to push it aside. One last thing to do in this problem, and it's a really important thing to do, and that's to state a conclusion. there simply is not enough evidence to reject the null hypothesis that the eggs are from the rare turtle species. So, our conclusion is that this biologist should take the eggs back to the zoo for incubation, because there is a chance, and probably a pretty good chance, that these are from the rare species. Always finish your problem with a written statement of what it is that you are concluding. And it is not simply the words reject H sub 0 or fail to reject H sub 0. That's an okay starting point, but you have to put it back into the context of the problem. And we would say that we fail to reject the null hypothesis because there is not enough evidence to say that the eggs are from one of the common species. They very well could be from the rare turtle species. We don't have enough evidence to say that they aren't. Here's another problem. A research meteorologist has been studying wind patterns over the Pacific Ocean. Based on these studies, a new route is proposed for commercial airlines going from San Francisco to Honolulu. The new route is intended to take advantage of existing wind patterns to reduce flying time. It is known that for the old route, the distribution of flying times had a mean of 5.25 hours with a standard deviation of 0.6 hours. 36 flights, there's N, on the new route have yielded a mean flying time, shouldn't have circled quite that big, should I have yielded a mean flying time of 4.90 hours. Does this indicate that the new average flying time for the new route is less than 5.25 hours? We will do this at a 5% level of significance. First, define the parameter. Mu is the mean flying time from San Francisco to Honolulu. X bar is the sample from these new flights. Our null hypothesis is that mu is equal to 5.25 hours. In other words, we are saying the new flying route hasn't made a difference. The alternate hypothesis is, yeah, it did make a difference. Null hypothesis is always status quo. Alternate hypothesis is always something's changed. And in this case, the something changed is that mu is now less than 5.25 hours. We are conducting a left-tailed test here, and that's because our alternate hypothesis was based on a less than statement, that mu is less than 5.25. Along with the fact that this is a 5% level of significance means that we are in luck if the z-score that we find in a moment is less than negative 1.645. If that happens, that would put us in somewhere here in the right tail. Or excuse me, the left tail. And if we get a z-score that is bigger than negative 1.645, that's an indication that we are not in the tail that we are interested in, and we would not be able to reject the null hypothesis. Find the z-score in the usual way. Our sample mean is 4.90 hours. Our assumed population mean is 5.25 hours. Standard deviation 0.6 of an hour based on a sample of 36 flights. So we will divide the denominator by the square root of 36. The result is a very negative number. It is negative 3.50. Did we land in the critical region? Did we go far enough over to the left? The answer is, of course, yes, we did. Because negative 3.50 is less than the critical value, less than the boundary that we were interested in of negative 1.645, we will reject the null hypothesis. Put it back into words. We are rejecting the null hypothesis. There is significant evidence to conclude that the flying time on the new route
is less than the flying time on the old route, the evidence is sufficient for us to make that conclusion at the significance level that we had defined earlier. Third example, and this one's going to be on you. A large company has branch offices in several major cities of the world. From time to time, it is necessary for company employees to move their families from one city to another. From long experience, the company knows that its employees move on the average of once every 8.5 years. However, trends for the past few years have led people to think that a change might have occurred. To determine if such a change has occurred, a random sample was taken of 48 employees from the entire company. Employees were asked to provide either the number of years since the company asked them to move, or the number of years that they have been employed if they have not been asked to move. For this sample of 48 employees, the mean time was x bar equals 7.91 with a sample standard deviation of 3.62. And again, I drew a little big there, so let me fix that. Let's see if we can reject the null hypothesis at the alpha equals 0.05 level. So the first thing you're about to be asked is, what's the alternate hypothesis? Well, I'll give you a hint here. There's nothing in this problem that suggests that the company's theory is that it had to be a lower average or a higher average, just that it has changed. And as a result, the test that we will be performing is not a left-tailed test, it's not a right-tailed test. Structure your alternate hypothesis based on the fact that this is a two-tailed test. So take a moment to work your way through this problem, and we'll come back together in a moment. You're off to a flying start if you realize that the mu that we are interested in is the mean number of years since the time that the employee last moved. We've already said that the null hypothesis is the status quo, that the average time that the employee has worked for the company since their last move was 8.5 years. Our alternate hypothesis is that it's no longer 8.5 years. It might be bigger, it might be smaller, but it sure as heck isn't the same. Because of that, as I said before, we are doing a two-tailed test, and that is because the alternate hypothesis has a not equal to symbol as its symbol of inequality. It's not less than, it's not greater than, it's either one of them. So mu is not equal to 8.50. At a 5% level of significance, Z sub 0 is plus or minus 1.96. If we can get a z-score that is lower than negative 1.96, we will reject the null hypothesis. If we get a z-score that is greater than positive 1.96, we will reject the null hypothesis. If we are somewhere in the middle, we fail to reject. Moment of truth. Did we get an extreme enough z-score? The answer is no. The x bar that we've been working with, 7.91, and the mu that we are working with, 8.50, subtract in the numerator. The denominator is the standard deviation, 3.62, divided by the square root of the sample size, square root of 48. We end up with a z-score of negative 1.13. And as a result of that, we fail to reject the null hypothesis. We've even got a nice normal curve drawn on here to show you where z is relative to the critical regions. We did not land in the critical region on the left. We did not land in the critical region on the right. We landed here. And that's not going to work. We're buried well into the region that is labeled do not reject the null hypothesis. And so our conclusion is that we fail to reject H sub 0. And as there's a conclusion to be made here, you always want to answer the question. We fail to reject the null hypothesis because there is not enough evidence to show that the mean time since the last relocation has changed. Here are your problems to work on. See you next time.